Hi everybody, we are now going to talk about regressions and how to access regression output. So our data frame is the MPG data frame, and here we have, among other variables, we have horsepower and the miles per gallon for different cars. And miles per gallon is how far a car can go using only 1 gallon of gasoline. So these are kind of old cars, so they do not get very far on 1 gallon of gasoline. But we are going to try to explain the variation in miles per gallon by using the information in horsepower, which means that we can make better predictions about the miles per gallon for a specific car if we know the number of horsepowers that this car actually has. So we see that we have 392 rows in our data set after removing 6 not a numbers in this horsepower column, and we need to define the x variables and the y variable. And we are only going to use one x variable. So this means that we have the equation y equals a constant plus beta x, which means beta times horsepower, or a slope times horsepower. And we need to add a constant, as we saw in the previous video. And here we add a constant to the x variable, which has this horsepower variable. And now we can see that we both have horsepower and the constant in our data frame, which we call x. And this horsepower will be explaining the will be how do you say it, related to the slope of the equation, and the constant will be related to the intercept of the equation. So to fit the model, we just use the stats model's OLS function, and we provide the y variable and the x variable data, and we want to fit this data to our modeler framework. And then we would like to get a summary of the regression result. So the regression result is a variable where we have the regression results, and this is an object. So it has different methods which we can access, among them the summary method. So if we just run this, we see that, well, we have an r squared of 0.6, and which means that 60.6% of the variation in the dependent variable, which is miles per gallon, is explained by the information in horsepower, which is the only independent or explanatory variable that we have in our model. And we see here that we have a constant, which is 39.9, and we have horsepower, which is negative 0.15. And this means that for a car with no horsepower, the constant is actually what we would predict for the MPG. So a car with 0 horsepower, we would, according to the model, expect it to go 39.9 miles for 1 gallon, which is of course a bit weird, because we do not have any cars with this with 0 horsepower. So this is an extrapolation. So we cannot really interpret this constant in a meaningful way. So that's why we call it an extrapolation. But the horsepower is a negative 0.15, so, or negative 0.16. So this means that if we have a car with one more horsepower, we expect it to go 0.16 miles less by use of 1 gallon gasoline. So, and in some previous videos, we have seen that to get the fitted values, the expected values of the dependent variable, we just take these coefficients and put them in a vector, and then we can take this vector and multiply it with the data matrix. So in this case, if we wanted to get the fitted value for this first observation here, we would take this this row times these coefficients, and we would take the first row in the X matrix here, which is 1 times 39, plus the second row here, which is 130 times negative 0.16. And then we would just sum up the two expressions, and then we will get the expected from the model value of the miles per gallon for this observation, this 0th observations. So, but how do you get a hold of the coefficient here? Well, you can add or you can access the regression results object params, and in params there are two objects, or two elements I should say. One is the constant, you see that here, and the other one is horsepower, and this just comes from the names of the data frame columns. So now you know how to access these parameters, these coefficients. So we just put this into a variable called alpha, and we just print the constant term for the regression line is alpha, and we are rounding alpha to digits. Okay, so we just run this, and we see that the constant term for the regression line is 39.9 miles per gallon. And we do the same for the beta here, the slope, and we want the horsepower, which was negative 0.16, and we want to print the model predicts that 1 additional horsepower changes the miles per gallon by, and we also round this number to 2 digits, and we remember to string cast it or typecast it as a string when we are printing, and we get the model predicts that 1 additional horsepower changes the miles per gallon by negative 0.16 units. And we can also access several other metrics from our regression output, and we have the R squared, for example, and we have the R squared adjusted, which always is equal or lower to the R squared. So this is the R squared adjusted, is often what we are looking at when we do regression analysis. So if we go here, we see that the horsepower explains 60.5% of the variation in MPG. Actually, the R squared is this or has this interpretation. The R squared adjusted is used to compare different models which have the exact same dependent variable and the exact same data data frame. So if we want to create predictions, we can just make a new variable called pred, and in this we get the predictions. Okay, so the regression results object, it has a method called predict, and we pass in all the observed horsepowers, and we are getting the predicted miles per gallons, which we put in a separate column, which is the predicted miles per gallon. So for example, for the first car here, we have that it has 130 horsepower, and by using that information, we have a predicted miles per gallon of 19.4. But we see that in our data, that car number 0 here had an observed miles per gallon of 18. So this guess is actually not far off, because if we had no information about anything, then we would just, if we had a new car, we would just guess the average miles per gallon for that new car. But if we get some information of the car, for example, the horsepower, then we can use the horsepower or the information from the horsepower to actually make a much better prediction. So, in order to actually plot the predicted line here, we have to sort the values of horsepower. So, and of course we say in place equals true because we want to change the source data frame. So this MPG, this data frame, has a method called sort values. We want to sort horsepower, and we want to change the order of the data in this data frame itself. So in place equals true. And then we just plot whatever we have in this data frame. And we see that horsepower is now sorted, and or the observations are sorted according to horsepower. And we go from low horsepower to much higher horsepower. And we can make a plot here of the actual observations. So you have observed a car with 50 horsepower and, for example, 27 miles per gallon and 75 horsepower and 30 miles per gallon and so on. And that is your data, okay? But if we are using the information in horsepower, we can actually make a guess here, a model dependent guess here of the miles per gallon if we get some information about the horsepower. So that's when we are making predictions. For example, if we are making predictions, we have a car which has 125 horsepower, and we would like to know, okay, how many miles per gallon would that car actually get, and we just go up here and we see that, well, this is our value for the regression line, and that is maybe 21. So then our best guess is actually that a car with 125 horsepower would get 21 miles per gallon of gasoline. And it's important to remember that, for example, if we have a car with 10 horsepower, we do not have any data close to cars with 10 horsepower. So we would not be able to extrapolate this line here to this few horsepowers. And the intercept is actually crossing the line where horsepower is equal to 0, and the intercept was here of 39. So it would cross the y-axis on 39. So this is clearly an extrapolation. And equally, if you're extrapolating on the other end here, for example, you have a car with 300 horsepower. We do not have 300 horsepower in cars in our data set, so that would be around here. But you see that this slope is or this line is downward sloping. So what would the our prediction be? Well, if we have 300 in a variable called HP, and we just use the predict method of the regression results object, and we have to remember one for the intercept, and then we have HP, and then we would like to get the first element in this result. So then we put that here, and we predict that a car with 300 horsepowers has a fuel economy of negative 7.4 miles per gallon, which is clearly not realistic, because you cannot have a negative miles per gallon. And you also see that this relationship between horsepower and miles per gallon is not a linear one. So here we would probably want to take the logarithm of, for example, horsepower and, for example, miles per gallon to make this scatter plot more a straight line.